In the previous lectures, we have started the modeling of the CCM operation of switched mode converters. Starting from this lecture, we are going to enter into the modeling of the DCM converters. So before we talk about the DCM model, let's first have a review on the CCM modeling of the switched mode power converters. So first, let's have a CCM review. So previously, we have derived the DC model of the switch mode power converter in continuous conduction mode. So here's the review of the DC circuit model. So for DC model, we can use a transformer to model the power converter. So here is the DC input. And here is the DC transformer. Coupling point. And we use this with the dashed line to indicate that this is a virtual DC transformer. The turns ratio is 1 to MD, which is the voltage conversion ratio of the power converter. And here is the load resistor. Output voltage is marked as capital V. And also, based on the DC model, we can introduce the small signal perturbation and linearize it. So we can derive the AC model of the CCM converter. So here I only put the AC kinetic model here. So canonical model means that different topologies can be unified into one same schematic. So we have the input source, AC, VG, cap. And in parallel with it, we have the current source, which is indeed controlled by the controlling parameter D. So the coefficient is J. And here we have another voltage source here. Controlling coefficient is E. And we have a AC transformer. The turns ratio for this transformer is also 1 to MD. And this is also a virtual transformer, not the practical or physical transformer. So we used a waveline to indicate that this is a virtual AC transformer. And on the right-hand side, we have the low-pass filter network with a effective inductance and output filter capacitor and load resistor. So here is the small signal AC output voltage, V cap. So this is a unified model, and the different topologies, they have different coefficients like J, E, and MD, and also the effective inductance. So based on this AC canonical model, we can derive the transfer functions of the power converter. So for the CCM transfer functions, so here, if we take the buck boost as example, so its transfer functions contain two parts. One is the control to output transfer function. So its control to output transfer function is denoted as GVD. So it has such a format of GD0 times a fraction. The numerator is 1 minus s over omega 0. Denominator is omega z. Denominator is a quadratic pole response, 1 plus q omega 0 plus s over omega 0 squared. The other transfer function is the line to output transfer function, which we denote as GVG. So it has such a format with the DC bias GG0 times a fraction. The numerator is 1. Denominator is the same as the control to output transfer function. Which is also a quadratic pole response with identical quality factor and omega 0. So if we look at the CCM buck boost example, which the expression of the two transfer functions are written here. So we can see that the GVD this transfer function contains 2 poles and 1 right half plane 0. And for this transfer function, GVG, it contains 2 poles. So actually, the 2 poles are identical for those 2 transfer functions. And before we talk about the analysis of DCM modeling, so let's first have an overview of the DCM features. So let's compare the behaviors of DCM model and the previous started CCM model before we analyze the mathematical expressions. So the first feature for DCM is that it is simpler. Simpler than CCM with reduced order dynamics. Specifically, it means that its transfer functions contains only 1 pole. So in comparison to the CCM, we can see that 1 pole and 1 right half plane 0, they are kind of approximately eliminated, but indeed they are pushed to much higher frequency. So one pole and 1 right half plane 0 are pushed to very high frequency. and such that they can be ignored. For approximated analysis. And the second feature is that in compared with CCM, DCM's steady state output voltage is not only depending on duty cycle, right? It is also strongly load dependent. So actually, we have derived an DCM voltage gain equation in the previous lecture. And in the following sections, we are going to also use the DC model of DCM operation to derive its voltage conversion ratio. You will see that there is a load component in the voltage gain formula. And the third feature is that for DCM operation, all converters, they might operate in DCM. Specifically for the light load conditions. Okay, so in this section, we have reviewed the standard model for the conventional CCM operation and also its transfer functions. We have introduced the features of the DCM transfer function and also its advantages. In the following section, we are going to go detail to derive and analyze those features.